my kids.
How far away do your in-laws live?
They live in Newmarket, so I left my house. That's on the way almost to Crawfordsville. So I left my house at 6:10 this morning to take him there and then go. I beat them to make them puke. I don't know. Like they're just sick. I don't know.
What town is it?
Newmarket. So that's like I live in Bainbridge, so I had to go almost to Crawfordsville. So like I went up 231 past Southmont. You turn right there at Southmont. Take him to Newmarket, and then I had to drive back here. So like my goal was to leave there no later than 7, and come back. So.
It's at like elementary schools. You get in trouble for missing school.
You can't. I mean, you shouldn't. It's so like, you miss so many days just like here.
But like, what do they do? Like, they can't really get in trouble.
I don't know. I don't know.
Because like when I was little, I never worried about like missing school. If I was sick, I just was sick. But now like you can't. Like if you're sick.
Yeah, I don't know what happens if you miss too much, but like I get a notification, like an email, just like, that said like unexcused from yesterday.
Maybe because elementary kids get sick more because they like pictures, so they're more like holding their fingers.
Maybe. Lick their fingers.
Well, Mrs. Hodges' kids, every time I go there, they're like stuck on their feet.
Yeah, Mrs. Hodges' daughter left the van door open all last night, and it rained in there. So like I was telling Mrs. Hodges this morning how Parker puked everywhere, and then she's like, Catherine left the door open to the van all night, and it rained. And Mr. Love's in there making copies. I said, Mr. Love, like, we're going to be the reason you never have children, because all you hear are all of our terrible stories
51 kids.
of how exhausting our children are. He goes, yeah, my dog's never caused me that problem.
I don't think he wants kids. Like, I'm just feeling the vibe that he just does not want kids.
I don't know.
But I have dogs.
Okay. Proving trig identities. The word proof seems kind of scary, but here's a big idea. A conditional equation is an equation that's true for only part of the domain. So what we've solved so far, when we solved equations in 5.1, we would say what values of x equals 0, right? And there's only certain answers. Pi and 2 pi and 0, right? An identity is true for all functions. So no matter what you could plug in here to sine squared plus cosine squared, any x value you plug in, it'll always give you 1. And so when we're proving identities, we're proving things that are true for everything. So the only way to prove them is to use the algebra idea of proof, the geometry idea of proof. You can't just plug numbers in and see if they work, because you can't check every number. Does that make sense? That's why we do proofs. You can't say, well, let me plug 1 in there if it works, or let me plug whatever. You can't check every number, so that's why we do proofs.
I have to write it out. Like,
We're going to write.
this.
No, that's right. I'm going to show you. What? Yes? Go back. Yes? No, sorry. I thought you had something to say. Okay, good. Okay, so this is what your book says the general strategies are, and then I have my own strategies I give you. But basically, when they give you a proof, they're asking you to prove one thing equals another thing. So it kind of looks like an equation, but it really just means, can you prove that this side equals this side? And so you're going to begin with the expression on one side. It doesn't matter which side you work with. We'll talk about that in a minute. The proof ends when you turn one side into the other side. So you know you're done when you have the same thing on both sides. Step 3 is the important step, the in-between steps, right? Like here's what should happen at the end. We should get that secant x cosecant x equals secant x cosecant x. Remember in geometry, like your last step you knew was like whatever you were supposed to prove? I know that's how it's supposed to end. That's not going to get you the points. The points come from the in-between steps. So here's kind of the important part. I need to be able to see what you do from step to step, which means you can't do a ton of work in your head. You have to show me plugging in identities. You have to show me the algebra. Show me where I can see it. Because you don't have to write out, I multiplied both sides by 7. Or I used the commutative property of whatever. Like in geometry, you had to say what you did. Here, you just have to show me. Okay? So let's just practice a few, and then I'm going to give you some strategies. So since I wrote it like this, let's have a goal. Let's turn this side into this side. How do you turn addition into multiplication, right? That seems like a magic trick. Here's a big clue. If you see addition on one side and multiplication on the other side, that probably means you're going to need to get a common denominator. So could we write tangent and cotangent as fractions instead of tangent and cotangent? We could. Do you want to write them as like 1 over cotangent, 1 over tangent, or do you want to write it as like sine over cosine, cosine over sine? Sine over cosine, cosine over sine. It doesn't really matter which one you choose, but I think sine over cosine is a better choice because why? This is what we want, right? And is secant and cosecant, those are the reciprocals of sine and cosine, right? So when we see that over here, let's turn these into sines and cosines and see what happens. So let's change tangent to sine of x over cosine of x, and let's change cotangent to cosine of x over sine of x. And here's the part you're going to complain about every time. I want you to write what it equals on the other side. Keep it lined up. So I want you to say this is going to equal secant x cosecant x. And no, you can't just put quotation marks. Write it down. But basically, we're not going to touch that side. We just want to turn the other side into that side. So this is what we did side 1, day 1. Can we get a common denominator on that side? Yeah. What would our common denominator be? Cosine x times sine x. And I'm going to go ahead and make it one denominator, which means over here, what do I have to multiply the top by? Right? And if you want to show that you're multiplying by sine x over sine x, you can. You don't have to. Sine times sine gives me sine squared. And then over here, I have the sine, but I need the cosine, right? So I have to multiply by cosine x. And cosine times cosine is cosine squared. And again, although people get really scared of proofs, I like these better than what we did in 5.1, because in 5.1, you never knew when you were done. Like, can I keep going? Is that my answer? I don't know. On here, I know when I'm done because when they equal each other. So I know I'm not done yet because I have to turn this into this. So now let's look at this. Do you see anything we could do? Sine squared plus cosine squared equals 1. That is a theorem that you should know, that I should know, so you don't have to show me that that equals 1. Like, you can just say your next step is 1 over cosine x sine x equals secant x cosecant x. Maybe I could just have left that as my final step, but since this is multiplication, you can't break up addition, I'm going to show this extra step here. And it's kind of really bad thing to do is not show me enough steps, all right? Like, I need to be able to see what you do from step to step and not be thinking in my head, how do they get from that step? So I always say if you're not sure if you should show the step, show it, right? It's better to show too many steps than to leave out steps. But this is kind of up to you if you would show this or not. But could I break this up as saying that this is the same as 1 over cosine times 1 over sine? Because I can break up multiplication, I can't break up addition. You see that we're about there? Because what is 1 over cosine? And what is 1 over sine? Cosecant. So I get that that is true, and you can do whatever you want. You can put a check mark. Check marks make me happy. Make me feel like I accomplished something. We could do a smiley face. You could do, what did you say? Right, true. Sometimes people do like this, or like this. I never remember which way it goes. This one? This one? This means like, in conclusion, or therefore, I don't know. Some proof language that we use. We use this in my class a lot. Therefore, proven, I don't know. Anyway. I don't care. You don't have to do anything. You could just leave it and move on. I like check marks because it makes me feel like I know I'm done. I did something. But that's the process, right? How do you feel about that? Not as scary as you think it was, right? So, over the years of doing these, I have some general tips that I like to give you. So if you get stuck, my advice is look at these tips to do these. Just like proofs in geometry, you're not ever going to learn how to do them if you don't try them. And so it becomes some trial and error here, but I try to give you some ideas of what to do. So I know you have this in front of you, but I'm going to cover them up. Work with one side at a time, particularly the more complicated side. Take the side that looks complicated and try to turn it into the other side. you may never do something to both sides, right? It's not like a normal equation. It's basically just trying to tell you to prove that this side equals this side. So you may never like add 7 to both sides or square both sides or multiply by sign. That's not a proof, right? And so you cannot do that. Number 2, look for those same tips that we did in 5.1. Look to see if you can factor it. Look to see if maybe you can get a common denominator with adding fractions. If you could square it into a perfect square binomial, or create a denominator that doesn't have addition in it. That's what that monomial denominator means. That's a lot of math words in there. You got to know your identities, especially the Pythagorean ones. Those show up all over the place in these, but even just the reciprocal ones, you got to use those. If you don't know those, you're going to really struggle. This is why I like these better. Look at what you're trying to get. If your answer has sines and cosines in it, use that. If your answer is in tangent, think about how you could get tangent. Remember which pairs match up in your Pythagorean identities. Remember the factoring, that kind of goes right up there with number 2. But remember that if you have a perfect square minus a perfect square, that you can factor. To do that, number 6 is listed as number 6 because it should not be your first choice every time. But remember that you can convert every trig function into sine and cosine. So if you can't figure out what to do, then you should try converting everything to sines and cosines. If this is your go-to strategy, you're going to make a lot of work for yourself. Because maybe the cool thing about these or the terrible thing about these is sometimes there's a proof that I can do in 3 steps, and you do it, but you take 12 steps to do it, which seems terrible, right? Sometimes I take 7 steps, and you can do it in 4 steps. And that's where it's nice, but it's also awful to grade those. You got to try these. If you're not attempting them, you're never going to get them. It seems like I magically know what to do every time, but it's because I've worked them out before, and I get stuck as well. I can show you my homework when I did the homework for this section. There's ones that I've just crossed out because I start something, it doesn't work, I cross it out, and I start over. And that's what you have to do sometimes, because I can't tell you every time what to do. I can tell you what to look for, but you have to look at it and just get better at trying these. So let's try a few of these that aren't so terrible, and then maybe one that's a little terrible. I don't know. Let's see. I just start with ones that aren't so bad to show you that those aren't terrible. You should work with the side that's more complicated, which means which side should we work with on number 2? Definitely the left side, right? We want to try to work this out to make it equal 1. So, any suggestions? Yeah, the Pythagorean identity. 1 plus tangent squared equals secant squared. Right? 1 plus tangent squared equals secant squared. And this is where I'm okay. If you know those identities, you can plug them in. If you're not sure, you could actually like replace secant squared with 1 plus tangent squared. I don't know what you want to do there. But I'm really okay with just replacing the Pythagorean identity with what it equals. So secant squared minus 1 would equal tangent squared. And notice they're using y's here. They can use thetas. They use all different stuff. You just use whatever they use for their angle. Now what? One strategy would be here. Cotangent is the same as 1 over tangent. And does 1 over tangent times tangent equal 1? In my Math 137 class, when we did proofs, we did one sort of like this. I think it ended up being cosecant times sine, and I told them that they should rewrite cosecant as 1 over sine to show they canceled out. And Aaron Cole said, isn't it just common knowledge that people know cosecant times sine equals 1? And I said, I don't think that's common knowledge. Maybe to you it's common knowledge, but I think you show a step, right? Show me that it cancels out. Err on that side. Okay? Number 3, I gave this one, it's not a hard proof, but I gave this one because here's what happens. People really want to subtract 3 over or subtract 4 over, right? Like you just are so used to moving things around. You can't do that. You have to work with one side and turn it to the other side. Number 3 is an example that I don't think it matters which side we work with. We can make either side turn to the other side pretty easily, but you aren't allowed to move stuff over. So if you want to take this side and turn it into this, you have to think about what can I do, what can I plug in, what can I replace to get that, or if you want to take this side and turn it into this, you have to plug stuff in. You can't just move stuff over. So, anybody want to pick a side and tell me what to do? Tangent and secant definitely go together in the Pythagorean identities, right? I just wrote it up there at the top. 1 plus tangent squared equals secant squared. So, what can I do? On which? You change this side? I think it doesn't matter either side. If we work with this side, all right, I like to work with this side on this one. But if you work with this side, can you tell me what tangent squared equals in terms of secant? What would tangent squared equal up here? Tangent squared would equal what? And you can substitute that in, right? So can you replace this with secant squared minus 1? And is that it? Like, do you get the answer from that? You get secant squared plus 3 equals secant squared plus 3. I don't know why I put 1. I worked with this side. I left the tangent squared. And over here I said, well, secant squared equals 1 plus tangent squared plus 3. And then look what I got. I got tangent squared plus 4, which means I made the other sides equal. There's no rule of which side you have to make equal the other side. Sometimes it's just easier to do one side or the other. Sometimes it's kind of your choice of which way to do it. But do not just like subtract 4 from both sides or subtract 3 from both sides, because that's not a proof. That's solving an equation. Okay? How do you feel about that? If the directions say verify the identity, then it will always work. Like, there's a way to do it. Your book likes to give you some questions like this that say, tell whether or not f of x equals sine of x is an identity. What that means is they want to know, does this equal sine of x? And they're saying it might not work, so I like to put a question mark over here, saying, is that true? They're asking, can you prove, does this equal sine of x? And it might be no. That's the only time it could be it doesn't work, is if the directions say, tell whether or not this is true. On your test, I won't give you any like this, but it kind of just gives you some practice of working out some easier ones, which is why I gave you these. So, any suggestions of what we could do with tangent divided by secant to see if that turns into sine of x? Change tangent to sine over cosine and secant to 1 over cosine. Totally an option here that we could do that. That is true. Tangent equals sine over cosine. Secant equals 1 over cosine. That's kind of a big mess, right? Like a fraction over fraction. It works though. You can do it.
I like multiplying.
Flip totally works. Also, instead of having to deal with that fraction, if secant's in the bottom, can you automatically bring it up and it turns into what? Cosine. That's another option, right? But it's fine to do it this way. So we would get sine x over cosine x. Keep playing, change flip would become cosine x over 1. So, is that true? Yeah, that's going to cancel out, and I'm going to get that sine x does equal sine x, so I don't have to put the question mark there anymore. And on this one, I guess we should say yes, since it's actually asking, does it equal sine x? Or just show it. Okay, let's try the last one. Which side would you choose to work with, left or right? I would definitely choose left, because I see parentheses there, which means what would be a good first step to take on this? Yeah, distribute. Multiply that out, and then go from there. And then maybe you already see something else you want to try. But if you see some kind of algebra you can do over here, like factoring or multiplying, distributing, that's a good step to try to make it turn into this. And so I'm going to get cosine x times tangent x plus cosine x times sine of x times cotangent of x. So the good news on this is we have something plus something on both sides, which is what we want. We just need it to simplify. So notice on this side we only have sines and cosines. So if I only have sines and cosines over here, does it make sense that we should change our tangents and cotangents in terms of sines and cosines? And hopefully stuff cancels? Maybe you did that in the first step, like you did that all at once, that's okay. As long as I can read your proof and see what you did, it's okay if you did that all at once. But I'm going to go through now, and I'm going to change tangent to sine of x over cosine of x. And I'm going to change cotangent to cosine of x over sine of x. And I think some stuff cancels, right? These sines cancel, these cosines cancel, and I get sine of x plus cosine times cosine is cosine squared.
That was so much faster.
Did you get it though?
Yeah.
See, there you go.
I just think you was like fast. I was like, and I did one on the
Oh yeah. So then you got a comment on there first, and then you got the right answer. So sometimes I have to tell this story just because Daniel Seacrest is still mad about it. Is sometimes I like to say you can do a backwards check mark like this because I said last year that left-handed people make their check marks backwards, but Daniel Seacrest informs me that he's left-handed and he does not make his check marks backwards. But my high school teacher, Mr. Chestnut, is left-handed and he always graded my papers and he put backward check marks all over them, and he said he did it because he was left-handed. So that's the only reason I say left-handed people do backwards check marks. But apparently Mr. Chestnut's just a weird left-handed person. So. He says it's easier. He said, ask your dad if it's easier to make a check mark backwards or if you're left-handed. That's what Mr. Chestnut told me. So, so I think that's it, right? I said you might want to start tonight, so then you can work on it tomorrow. 5, 7, and 10, I believe the directions are just does it equal sine of x, which means you might get no, and it feels wrong when you get that it doesn't work. The plan is Thursday we will talk about a good amount of these, right? Not all of them, but we will do from 12 through 33. What is it? That's 8 problems. It seems like a lot, but it's really not. That's 8 problems. I guarantee of those 8 problems, we'll do at least 3 of them on the board, just to kind of reinforce what to do, and then we'll do some more examples. I'll give you some more problems. But try them.
If it's like a real big struggle after I did
Yeah, I'll be here.
I don't know.
But just try them. My advice is if you get stuck, try something, and if it doesn't work, don't erase or like leave what you have there so that I can look at it, right? We can see where it is. And my advice is save your eraser if you do want to start over. Like just put a line through it and go on, because sometimes you end up having it right to begin with, and then you erase the whole thing and you're like, that's what I had first. Whereas if you just kind of put a line through it, I can still see that and go from there. So that's my advice, but it's up to you on how you want to do it. But if you see fractions, probably get a common denominator. If you see stuff that's Pythagorean in these, then you can want to use that. You might have factor on these. But we'll see. We'll see how it works. Just try some stuff and see where it goes. And then we'll get to some crazier stuff. But it is try time day.